All right, let's move on. We just talked about sequential logic, right, time analysis, and clock. Let's come back to some of the basics before we build up the microprocessor. Let's come back to binary arithmetic. We briefly talk about this, right? Talk about the 1-bit right adder at a certain point, but I never sort of formally introduced how we do the addition, right? Subtraction and multiplications. So let's look at how it's done. First, a quick reminder. We had these. We have been seeing these binary values, right? Binary numbers a lot. But what we have defined so far is unsigned, right? So far we have never talked about how to represent negative numbers. For unsigned numbers, this is relatively straightforward. Right? For a 3-bit binary value, we can basically represent up to 7, right? So this is the corresponding decimal value. This is I think that you guys know this very well already, right? And basically we have this positional encoding, right? And for MSB in this case, we have 2 to the power 2, right? This is the weight on the MSB. We will see soon, we will see pretty soon, we have to change this to represent the negative values. Right? We can also represent fractional values as well, although I don't think we have covered this so far. The trick is, just like how we represent the fractional values in decimal systems, we can also introduce this binary point, right? Like this. This is a binary point, not a decimal point anymore, right? Because we are living in this base of 2 system. Once we define this binary point, we can associate the position, right? Bit position with each digit or each bit. For the things to the left-hand side of the binary point, right? These are the things that we are already familiar with. Right? We associate this index or position with 0, 1, all the way to n-1 in this case. But for the things to the right of this binary point, we will use a negative index, right? Starting from -1, -2, right? All the way to this arbitrary number, right? -n. Once we have this defined, once we have index defined, we can just use the same positional encoding. Okay? So for each bit, right, we look at its index and we associate weight according to the index. Right? We basically, in this case, if there's a bit I, right, for bit I, the weight is 2 to the I. This I can be either negative or positive or 0. Okay. Hopefully this is very straightforward, right? If this is the case, then just tell me what exactly is this number? What is this fractional value? Very good, right, Ethan? 5.125, right? Why is that? First, this part, the integer part is straightforward, right? This is still unsigned, right? Still unsigned. This is a 5, 101. Okay, then we just need to look at the things on the right. And this one is a 0. We really don't care, but the corresponding weight is, right, for this place is 2 to the -1, right? And the second 0, again, since this is 0, we don't really care, but this is 2 to the -2. And this one, the weight is 2 to the -3, which is 0.125, right? 1/8. And in the end, we have 5.125. Okay, so this is how we represent fraction values. This is sort of a fixed point. This is a so-called fixed point format. So where we fix the position of the binary point. Later on in some other classes, you guys may come across a much more sophisticated mechanism called floating point. This is used a lot, okay, in the actual processor. Right? So where this binary point, the position of binary point can float. Basically, hardware will do the normalization dynamically. If you have already used some languages like C or Java or Python, right, by default, those the real numbers will be represented in the floating point format. But there are actually a lot of advantages for fixed point as well. But this is not something that I'm going to discuss in this class. Right, so this is the fractional values. Now let's look at addition. Again, very intuitive, right? Very similar to how we add up the decimal numbers. We line up the digits, we align them, Okay, and then we just do a single pass, right to left. Okay, we add up each column, right? We do a single pass from right to left, and then we propagate a carry. Okay, so for the first case, let's just do some quick exercises. I already told you the corresponding decimal values, right? You guys should verify whether my answer is correct or not. Okay, this one is straightforward, right? We just add up this two per column. We add up the corresponding digits. Right? This is 1, 0, 1, 1. Okay, of course, this is 27. Okay. Next one, this is where we have some more interesting. Okay, I already animated, but let's look at this, right? So from the right, this is so-called LSB, right? The rightmost column. 1, right? This is 1. And second column, we are adding 1 plus 1. We're doing 1 plus 1. 1 plus 1 give us 1, 0, right? 1 plus 1 is supposed to give us 1, 0. For this binary addition to work, we keep 0, right? We keep the LSB, right? For the sum part, and then 1. We put 1 on the carry, right? And this carry, really, each carry means a 1. So then for the third column, we are re-adding 1, 0, 0. Okay, so that's where we have a 1, right? And 1, 1. Okay. All right, can you guys do the third one? Just tell me what is the resulting binary string. Don't look at the decimal value. Okay, very good. I think you guys are giving the same answer, but let's just quickly go over this. First, right, rightmost column, 1 plus 1, we have a 0 here, and we propagate the carry, right? Then over here, we are doing 1 plus 1 plus 1, right? Just want to be clear here. So there's a carry, so this is a carry, right? Doing 1 plus 1 here, right? 1 plus 1 plus 1. So which should give us 3, right? In binary, it's 1, 1. So that's why we keep a 1 here, right? In this a sum row, and then we have a carry to the next column. Then we have 1 plus 1, right? Again, we have 0 here, and a carry, and another carry. Right? In the end, we have the string, which end up to be 18. All right. Any questions so far? Okay, I hope this is very clear. Okay. How about negative numbers? Okay. So far in all of those, right? So these are all unsigned, right? All positive or non-negative. How about the negative numbers? One idea is to use this so-called signed magnitude representation, where we basically add one more bit, right? Think about sign, right? Sign either plus or minus. This also can be encoded in binary format, right? So why don't we just do that? We use we allocate the actual sign bit, right? We use 0 as to indicate positive or non-negative, right? And sign bit 1 to indicate negative. So then we have, right? So let's say, we use this format, right? Sign magnitude format. We use this one as a sign bit. Then the first one indicate 1, and the second one indicate -1. Right? This is fairly straightforward, right? This is also fairly natural. But what's wrong with this format? First, the nice thing, this is very natural, right? We have the symmetric range for the negative part and also non-negative part, right? So this is the range that we have using this kind of a system for n-bit number. But what's wrong? So there's some redundancy, right? If you do this, what's the redundancy? Yeah, very good, right, Jacob? Right, so we are wasting, so for a 3-bit number, we are actually wasting, 2 encodings, right? For a single number, which is 0, as you just pointed out, right? We have actually +0 and -0. This is already kind of annoying, right? Because somehow we have to distinguish these two in some cases, right? Unless they introduce some ambiguity and plus 0 or minus 0. And we really don't want to have this kind of redundancy, ideally, right? We want to use this, right, the actual encoding to represent something meaningful and useful. But let's say, this is not a problem. Right? Let's say we just treat 0 specially. We have a special circuit to deal with this. This is fine. Okay. There's actually something else that makes this even more annoying. Think about the binary addition that we just talked about, right? If you do this, right? If you do this, if you add up +1 and -1, right, over here, somehow we don't get a 0. If you just follow the procedure that we just defined, right? We add things from right to left, and we propagate the carry. What's wrong here? So somehow we get, well, what is this in this format? This is a -2, right? It's -2. It's not a 0. So the problem here is that really the sign bit, right? They are so special. We cannot just treat it as the same way, right? When we do this kind of addition, we have to have a special circuit to treat the sign bit, which is again annoying, right? That means all of a sudden, right? We actually need two separate circuits, right? One for adding up the unsigned numbers, right? One for adding up the signed numbers. This is not ideal. I hope you guys agree. Right? What's the fix? The fix is actually pretty remarkable. And it may seem like a hack at the beginning, right, to you guys? But I want to point out this is really elegant. So this is the encoding that we are going to use. Right? So instead of using 100 to indicate -0, so we're going to use it to indicate a negative number. Okay. First, I'm actually laying out this in a circle intentionally. I'm going to explain very quickly. So let's see, right? So for the non-negative numbers, right? So these are the ones that we are familiar with, right? Okay, 0, 1, 2, 3. No surprises here. But here, when we increase to 0, 1, 1, right, by 1, we have this like a wrap up or wrap around. We end up with -4 here. Okay, we will use 100 to indicate to represent a -4, and then we keep, right. So then the rest is the same. Okay, we just do +1, right? We get -3, +1 again, -2, -1, and we circle this around until we hit this wraparound point. Okay. So one nice thing about this is, again, we don't have this redundancy, right? This 100, right? So this one is a reserve, right? This is a preserve for another number, -4, which is nice. Again, this seems like a hack, right? But what I want to convince you guys is this one is actually very systematic, and this is very sound. This is not something that we are gonna talk about too much, right, in this class, but there's something called modular arithmetic, which is which underpins what's going on in this case. Like really -4. Okay. By modular arithmetic, I mean I'm using this sign, right? Modular operator. So really, in this case, we actually are doing a modular arithmetic with by doing this. Okay, -4 is actually -4 modulo 8 is actually 4. Okay, 4 is 100. Okay, the nice thing about modular arithmetic is x plus y, right? Modulo 8 is the same as x modulo 8, okay, plus y modulo 8. And so basically the regular arithmetic will just work. Okay? And this modular operation is implicit actually. Again, I'm not gonna get too deep right into this, but I just wanna convince you that this is not a hack. This is not just an ad hoc solution. This is fairly sound. Okay, if this is still not too clear to you, let me try to explain it in another way. So the encoding can be represented this way, can be interpreted this way. So really, when we look at the MSB, we assign a negative weight like this for the highest bit. In this case, we have 3 bits. Right? We will assign the MSB with a weight of -2 to the 2, which is -4. Okay. In general, for n-bit system, the MSB will carry the weight of this, which is -2 to the n -1. Okay, if we do this, right? If we do the math here, just want to verify, right? For -3, you can see here, we really have, right, 1, this, right? We do this. This is 101, right? Which is -2 to the 2 plus this, right? And this is indeed -4 plus 1, which is -3. Okay, this is the system that we're going to use for the rest of this course, and also this is a system that's being used in most of the modern microprocessors. This is called 2's complement. Okay, 2's complement representation. In many cases, we'll just use this shorthand 2C. Okay, 2C. That's the shorthand. C means complement. Any questions about 2's complement? Again, really the encoding is basically a circle, right? And the modular arithmetic basically operates on such circles. That's why I drew a circle here. And the key thing is the weights. Right? The weights for the MSB is a negative number now. All right. So if this is clear enough to you guys, maybe I can ask you a question. Can you guys tell me for 5-bit, over here, maybe just do 4-bit, since I'm showing you 3 bits. 4-bit 2's complement number. What is the most negative number and what is the most positive number? 4-bit 2's complement. Very good, right? -8 to 7. See here, the most negative number is this, right? And if you plug in n equals 4 here, you get -8. And this is something to remember, right? So with 2C, with 2's complement system, the range, right? If you look at the negative part and the non-negative part, this is sort of not that symmetric, right? It's not like -8 to 8. It's really -8 to 7. This is something to remember, because we are using one of it's a -0, right, to represent a more negative number. That's why this appears less symmetric. Okay. And the nice thing about this is the regular arithmetic, right? Like addition, will just work without any hacks, without any tweaks, right? For example, in this case, if you just add up +1 and -1, right? -1 is 111, okay? And then we get a 0, okay? How about the 4-bit? 4-bit -1, what is that? This is 3-bit -1. Anyone knows? 4-bit, right? So we have 4 ones. Okay. All right. And with this 2's complement representation, right? Just want to repeat some of the things that I already covered. Right? If you look at non-negative part, that's pretty much the same. Okay, with the things that we already come to love, right? It's just that for the negative part, we have to do some special treatment if we're not that familiar with. Of course, later on, if you are, when you get comfortable with this, right, in many cases, if you ask you guys to write down a negative number, you don't have to go through this step. But let me just show you some tricks first, right? Some techniques to convert something that you're already familiar with to this 2C representation. So for a negative number, we actually want to first, if you already know, right? So what is the corresponding, for the corresponding non-negative number, right? You already know the corresponding binary representation. So you can easily get the negative form. And the way to do this, you flip every bit and then just add 1. Yeah, Ethan, what's the comment? I actually, oh, cool. All right. Okay. So given a positive number, right? Given a positive number like 001, to get a corresponding, so let's say we already know this, right? But we don't know, you don't remember what's the -1. So this is the procedure. So first we flip, okay? We first flip all the bits and then just do a +1. That's how we end up with this 1, 1, 1, right? So this is the step. And later on, most likely, or actually maybe this is already a sign. I'm gonna ask you guys to prove this. I'm gonna ask you guys to prove these steps, right? This conversion is indeed sound and correct. Okay, but let's just first look at some concrete examples first, right? This is how we get -1, right? We first start with +1 and then flip everything, then do a +1. Okay. For -9 over here, again, we first get the binary string for 9 or +9, and we flip all the bits. Then we do a +1 on the LSB. That's how we get the binary representation in the 2C format for -9. Okay, so for now, just memorize this. Okay, so these are the steps. We are gonna show later, like why this is correct, and I'm gonna ask you guys to prove it. Okay, slightly more complicated example over here, right? Again, we are trying to get, right, the -1, right? The 2C representation for -1. This is X, right? This is -X. We flip and then +1, right? This is what I just told you. But here's a shortcut. The shortcut is instead of doing the plus, for doing this this binary addition, this is sort of error prone, right? So in some cases, we end up with some mistake. There's a much quicker way to do this. Actually, all we need to do is by following this step. So we want to copy the bits from the right to the left up to the first one that we encounter. And then we flip the rest. What does this mean? So if we look at this example, okay, I'm saying that we scan this binary string from the right to the left until we hit the first one over here. Okay, so up to this point, we don't do anything. We just copy down the string. We just copy down this part. Okay, this is intact. We don't do anything. And for the rest, we just flip. Okay, for the rest, see here, this is flipped. Any idea why this works? This is the trick, right? This is the shortcut. Right, so very good. Jacob, there's actually a carry, right? So you flip the whole thing and then do a +1, okay? You will get this carry, right? And then you will have, basically you end up with the same thing anyway, right? That's but try to convince yourself, this indeed works, right? See here, okay? When we flip all the zeros, right? Over here to ones, and then do another +1, these zeros will be flipped back to zeros again in the end, right? So that's why we don't want to do this redundant work. Let's just copy them down. okay, and only flip the necessary bits. Okay, this is why the shortcut works. All right, so this is how we get minus x if we know x, right? We know the representation for x. Any questions? Okay. If not, let's also look at how do we do the conversion, right, from binary to decimal. This is very straightforward. Okay. One way to do this is let's just do this, positional system, right? The positional weight system. We just add up the weights, and that's it. Another way to do this is if we do see that given a binary string in 2's complement format, if this is a negative number, right, meaning that MSB is 1, let's just flip the sign first. Okay, meaning that let's just look at the right. So let's just try to take the complement, 2's complement, to get a positive number first, and then follow the whatever you guys already know. Follow the step that you already know, and to get the corresponding minus x. And in the end, you'll flip the sign. Okay. To be more concrete, right? Given this number, what I'm saying is that just get a minus x. Right? Just get a minus x first. You follow the same step, right? Flip all the bits and then do a +1, or do the shortcut, right? Copy over the things on the right until you hit the first one, and then flip the rest. So get the minus x. Then you're trying to translate the minus x to a decimal value. In this case, it's 26. And then eventually flip the sign again, right? That's how you can convert a bit to its complement number back to a negative number in decimal format. Okay, so this is actually not too interesting, right? There are many different ways of doing this. Hopefully this is clear enough. Right? Next one is the opposite, right? So how do we convert a decimal number to binary? This one is slightly more interesting. Actually, there are two ways of doing this. One way is to do the decimal to binary conversion using the so-called division method. Okay, I'm not going to read this line first, but I'll first show you how this is This is done in an iterative fashion. So basically, given a decimal number, what we want to do is we try to divide it by 2, and we keep doing this. Okay? And then we keep track of the remainder of the division. So in this case, we have 104, right? And we divide it by 2. Of course, we get 52, right? And then we remember the remainder. The remainder in this case is 0. Then we just say that B0 is the LSB, the least significant bit is 0. Okay, and then we keep doing this iteratively. We do it on 52, right? Then we get 26. Again, the remainder 0, and then we divide 26. We get 16. Remainder 0 again. So that's where we keep track of the remainder, and then just write down the bits one by one. And we just keep doing this. This one over here, 13 by 2 is we get a 6, but now the remainder is a 1. That's where we have our first one. Okay. Again, this is iterative. We keep doing this until we divide up everything, until we hit a 0 in the end. Okay, until we hit the quotient becomes 0. That's how we get the binary string. Okay, so this is one way. This is a so-called division-based method. Okay, 0, 0. The way to read it is really, this is the LSB, okay? And this is the MSB. Actually, this is not yet. We need to append one more 0. Okay, we actually need to append one more 0. This is a positive number, right? We need to append a 0 for 2C. Okay, this is the binary string. We append the 0 over here. Any questions about this method? Okay, there's actually a shortcut also for division method. If you don't really want to keep track of the remainder, right? This is just one trick. Let me just quickly mention this. What do we have? we have 104, right? 104. One way to do this is, again, we do division, we divide it by 2, but we put this number on the right-hand side, okay, right-hand side, and we divide it by 2. That's where we get 52, right? In this case, I'm saying you don't need to keep track of the remainder. So let's just keep doing this. Okay, 52 and then 26, right? And 13, right? Divide again, 6, 3. Okay. What do you have mentioning? Right? 1 and 0. Okay. So once we have this sequence, so the moment you have this sequence, then you're actually pretty much done. So all you need to do is you look at each number and check, is this even or odd? If this is even, we get a 0. 0, right? Even again, 0. This is odd, right? 1. This is even, 0, right? Odd, 1, 1, 0. Okay. So let's compare this to same thing, right? 0, 1, 1, 0, 1, 0, 0. Same thing. Okay. This is how division method works, and this is the shortcut. Hopefully this is clear, right? So really, we are basically keeping track of the remainder implicitly by just looking at whether it is an even number or odd number. That's it. Okay. Any questions? Okay. Now let's look at another method. So this is where, with the division method, we are trying to derive the binary string from LSB to MSB, right? From the right to left. There's another method where we can derive this in the opposite direction. We can try to derive it from MSB to LSB. Is it from left to right? What are you asking?
Yeah, when you do like 13 divided by 2, shouldn't the 1 be under the 6 instead of under, or when you do 6 divided by 2, shouldn't there not be a 1 under the 3? Or maybe I didn't really understand.
I'm just saying that we are keeping track of so this is actually really the remainder, right? When we do 6 by 2, the remainder is 0, right?
Oh, so you put the remainder under what you were dividing, not the result.
Yeah. Right.
Okay, got it.
Right. Right. Because what I'm saying is don't worry about the remainder, right? Just write down the numbers and then just read whether this is the odd or even. That's it. Okay. All right. There's another method called subtraction. This is a subtraction method where we subtract the power of 2. What do I mean by this? Is again, let me give you this same number. So instead of doing the division, so what we are trying to do is let's try to find the closest power of 2. Okay. In this case, if you look at 104, right, the closest power of 2, which is no greater than 104, is 64, right? What is the next power of 2, guys? The larger, what's larger than 64? What's the next one? Very good, right? So both of them are next to 64, right? The one that's larger than 64 is 128. Okay, that one's already larger than 104. That's why we don't want to use it, right? That's why we pick 64. So the moment we have 64, okay, then all we need to do is we try to find out the index of the bit. This is 2 to the 6, right? 64. Then we just insert bit 6 to be 1. That's it. Okay. And we are done with the first iteration. This is also iterative method. Then we do 104 minus 64, and we get 40. Okay, this is the first step. Next step, we work on 40, and we try to find the next, right, the power of 2 value, which is no greater than 40. In this case, this is a 32. right? And 32 is 2 to the 5, right? That's where we set bit 5 to be 1. And we do the subtraction again, we get 8. Okay. And we're done, actually. Right? So with 8, it is already a power of 2, which is 2 to the 3. Right? Then we already have the ones in the the binary string. All we need to do is to fill out the zeros. That's it. Does this method make sense? What are we trying to do here? Intuitively. Anyone, any guess? So what we are doing here is, if we translate, right? We are basically, in this case, we are reversing the process of the binary to decimal translation, right? So if you think about this binary number, how do we translate it into a decimal number? All we want to do is pick out the ones, right? And this is 8, right? This is 32, and this is 64. And we add them up, right? That's how we get 104 when we do the translation the other way around. All we are doing here is we just try to reverse the process, okay, when we convert decimal to binary. Okay. Add binary, right? So Amanda, you're right. Okay. So basically, this is what we are doing. Okay, so these are the two popular methods if you do this by hand. Right? Okay, so I want to quickly cover a few more things. One is the so-called sign extension. So this is where, in some cases, we do want to convert a number, binary number. This is a 2 to the C, right? 2C or 2's complement number with a smaller bit width to something with a larger bit width. All we want to do is to basically append the. Okay, Zach, do you have a question? Looks like you're writing on my screen, which is cool. What we are doing is we are, right, so trying to do so-called sign extension. So when we try to convert a 4-bit number into an 8-bit number, all we want to do is to append the sign bit on the left-hand side. Okay. In this case, we have a 0, right? We extend it to 8 bits, we just append 0 on the left-hand side. If you have 1, we append 1's, the sign bit, right? Really, this still means a sign bit, right? 0, 1. Into C, you can still just read them, and you know like whether it's a negative or non-negative number. And you append the sign bit like this, okay? And this just works. I may also ask you guys later on to prove, okay, in a more formal way, why this is correct, right? Why sign extension is correct. Okay. All right. Okay. Why do we care about this, right? Why do we care about sign extension? The reason is that in many cases, we do need to add up fixed size numbers in microprocessors and CPUs. In most cases, right, with the common, right, the modern day CPUs, we are usually dealing with 32 bits or 64 bits. Right? So these are the size that we use in our memory system and also inside the compute engine of our CPU, which is something that we can touch on later on. Okay, this is not too important right now. Okay. But what I want to mention is, indeed, if we do want to add up fixed size numbers, okay, in our CPU. That's where we have to deal with certain issues. Certain interesting issues may pop up, okay? Like, okay, some of the things I'm going to show you very soon. First, fixed size addition, right? Let's assume that we have n, a 4-bit number, not 32-bit, not 64-bit. Those are too complicated, right, to do to work on, right, by hand. Let's just focus on the small bit width. So 4 bits. If you look at this, right, so these are just some more examples for adding up 2's complement numbers, right, by hand. None of these are too interesting or too surprising. Okay, you guys should just check them out offline. But I want you guys to focus on 2 things. I think this is also related to some of the comments that pop up on the chat window. although I did not address them right away. Okay, let's look at these two cases. Any surprises here? Are they correct or wrong? And I'll most likely ask you guys to do a quick quiz at the end. Okay, make sure that you follow these couple slides. These are wrong, obviously, right? 7 plus 6 should not be should be 13, right? How come this is a -3? And -7 plus -4 should be -11, right? How come this is a 5? Something's wrong here, right? Oops. Why is that? Why is this wrong? Wraparound, overflow. Okay, very good. Right. Basically, the intuition is they are just out of the range, right? See here, this is supposed to be 13, right? This is supposed to be -11. Can we represent? What can we represent? What is the highest value that we can represent with 4-bit 2C, 2's complement? You just discussed that, right? 7. With 4-bit, we can only represent up to 7. So that's where this wraparound is happening, right? This overflow is happening. Okay, so that's why we are seeing a -3. Same thing here, right? This is -11. This is 2 negative, right? Because we can only represent up to -8 with a 4-bit value. Again, in 2's complement format. That's what we call overflow, right? With overflow, this is something that we have to catch later on, right, in our microprocessor. But first, let's just explain what exactly is our overflow, right? So this is where, if we are adding up 2 positive numbers or non-negative numbers, and then we end up with a negative number, or the opposite, right? Then we are adding up 2 negative numbers, and we end up with a positive number. So that's where something obviously is wrong, right? But let me ask you a quick question. How about this? This is what we are doing, right? Well, if we do this, if we add up a negative value with a positive value, do you think we will ever have overflow? No, right? No, very good. Okay, if we are adding up 2 values with different signs, you'll never have an overflow. Think about why that's the case. If this is not clear, I can explain it later, maybe in the next lecture. Okay, so overflow occurs before the quiz. Okay. Let me just repeat some of the things that we already mentioned, right? When the sign, right, of both operands are the same, but the sign of the sum is different, that's where we have overflow. And there's actually a pretty neat trick to capture the overflow in the hardware. This is something that we're going to look at later on. That's where we check the MSB, the carry into the MSB and the carry out of the MSB. And we can just do an XOR. So that's how we can detect overflow in a very cheap way in the actual hardware. Okay. Think about why this is the case. But any questions on when do we have overflows? How does overflow occurs? It's really about out of range, right? So basically certain numbers are either too negative or too positive. Right? They are basically too large to represent with this fixed size representation. Okay,